So in this video, I told you that we would talk about the preference of O and P and what goes into that decision-making process. When we form these reactions and these products, I can draw them, I can represent them, I can name them, I can feel all smart when I do it. But what if the question asks me, which one's the major product? Can you identify which one the major product is? And the issue here is that it's more of a complicated type of answer. There's not one way that I can tell you to go with. So we'll give you two general kind of concepts. And other than just generally speaking, we will not be forced to do this type of decision-making process in these example problems. So they keep this pretty simple. They keep it very straightforward. And it's just something that we got to keep in mind as we work with O and P. So here's the thing that goes with O and P. All right, so let's say that I have a benzene, and this benzene, let's say, is an OH group. Well, I've got a decision that that OH group could be ortho, which means the new incoming group could go there, or it could go para, and that means the incoming group could go there. But that's not really the only thing that I can write down, because I could also do a ortho on that side. So due to probability and due to statistics, I have two orthos on these benzene rings. Two ortho positions. So I've got 2 times that I could form an ortho compound, and my paras, due to math and probability, I only have 1 para position that I could form. So out of these 2 options, what we can say is that ortho has on its side stats. Statistically speaking, ortho groups should be able to form in a higher percent yield. And that's because there's more opportunity for it to form as an ortho group. Now, what complicates this a little bit is the size of the groups. The size of the groups could start determining that ortho is not an ideal position. What does that even mean? Okay, well, let's take a look. Let's say that I didn't add an OH group here. Let's say what was on here was like a carbon, 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 carbon group. Oh, that size. That's right. If I look at this group that's attached onto this benzene ring now, look at this. The thing is pretty bulky. It's fairly large. And if I have an incoming electrophile that's going to come in and attack to an ortho spot, boing, it can't really get in there. And if it tries to go onto the other side, it can't really get in there because that bulky group is taking up size, it's taking up space, and it will prevent that group from easily getting to that ortho position. So this electrophile says, fun. If it doesn't want me at the ortho position, I'm going to go somewhere where it's easy to attack, and bing, it's right there. It's at the para position instead. So if we have big, bulky groups, it really forces these reactions to give me para products. But if the groups are fairly small, nothing special about them, ortho will form higher because statistics tells me that there's a higher chance of it getting formed. All right, so here's an example. This is toluene. Toluene's pretty simple. It's just the CH3 group, right? That's it. Just the CH3 group. They like to use this example because toluene is a O and a P director. So here we see the ortho getting formed, and there we see the para getting formed. And if we take a look at the yields of each one of the O's and the P's, and we calculate that percentage, well, ortho, out of the 3 spots that nitro could go to, ortho takes up 2 of 3, which is about 66%. And look at the percentage that actually forms. Pretty darn close. And then para, only 1 out of 3 chance of getting formed. And what's 1 divided by 3? That's 33%. And bam, that's really, really close. 39% instead. So here's an example of where statistics pretty much decides the answer to this. 61% we will get ortho nitrotoluene, and 39% we ended up with para nitrotoluene. Okay, well that was with methyl on a benzene. So now let's change it to an ethyl on a benzene. How does this really play a factor, if any? Well, ethyl is still an R group. Ethyl is still an O or a P director. So this is the ortho and this is the para. Both of them still form. We write both of them down. Out of these 2 choices, though, look at what happened to your percentage. The ortho percentage went down and the para percentage went up. It's now a pretty much 50-50 split. Why is that? Well, that's because ethyl is a little bit bigger. Ethyl is bigger than methyl. So this ethyl group takes up more space. And it's harder for the nitro to get into the ortho positions. It still can do it. And it does it 50% of the time. But it's a little bit more difficult than that simple little methyl group. So the remaining of the time that it can't get in there because it's hindered, and that's what this is all about, it's hindrance, the nitro will go on the para position when that forms. So 50-50 split. All right, well now let's take a look at my tert-butyl group. Now, CH3, that is basically this group. It's just drawn out. The one on the top is a condensed form. The one on the bottom is it fully drawn out the way that it's hooked up. So this tert-butyl group, it's called tert-butyl. You should have learned that from Chemistry 251. Butyl, 4 carbons. 1, 2, 3, 4. Tert, because that's a tertiary carbon right there. It's attached to 3 others. Okay, so tert-butyl, well, that's big. That's bulky. That big bulky group is going to have a nitro come in and whoa, bing, off it goes. Over to the other side, bing, off it goes. It's not going to work. It cannot get into the ortho spots because the tert-butyl group is so bulky that it really fights against that incoming group at those locations. So nitro just gets fed up and it says, fine, I'll just go where I can go and I'm going to do it the easy way. And then 82% is going to be the para form and 18% will be the ortho form. We have drastically changed which is preferred. It is no longer statistics. I don't care what statistics say. If that nitro group cannot get into that position, statistics is just numbers on a piece of paper at that point. It's got to have accessibility. Nitro has to have access to the ortho spots in order to form the ortho spots. Statistics doesn't mean anything. But don't tell a math instructor that I told you that. All right. Something else that we also want to keep in mind. Here we see a reaction. The reaction is a benzene with an OCH3 group. So this is an OR. The OR group, that oxygen's got some free pairs of electrons. Therefore, that's an activator, and it's probably an ortho and a para. And it is. So here we see a para, and here we see an ortho spot. Now, when we add bromine to this, notice what they did here. It's a slight change. I'm not really picky about this type of thing, but if you notice, they left off FeBr3 as a catalyst. And the reason that they did that is because it's really not needed. Bromine, the halogenation, is really one of the easiest reactions that go forward. And in addition to that, what we've done now is that we've added an activator to the benzene again. So benzene and the halogen reacted quite well, but benzene with an activator group reacts with the halogens even more so. And we don't really need that catalyst in order for that to go forward. Now, if you always write the FeBr3 up there, I don't really care. I'm going to give you credit that because I know what you mean. And adding FeBr3 is not going to change anything. It's going to be okay. You're still going to get the ortho and the para products as they've listed in this reaction. It's not a big deal. So if you do add it, whatever, I'm going to give you a check mark because you know at least what you're talking about. So that's one of the exceptions that we need to at least address. And that way, when you see this kind of thing written in a textbook and you do not see the FeBr3 that shows up here at the very top, don't come to me and say, but why did they not write it? That's why I didn't give you a product. Balt, no, we've already discussed that, right? If they don't write the B or FeBr3, it means the reaction is still going to go forward. It's just not needed. So don't use that as an excuse in order to give me a wrong answer on a test question. All right? Next, the other thing that we need to talk about is that we can also add these in multiple steps. Huh? Okay, well, kind of let me do this example problem for you instead of just reading it off of a slide. All right, here we have a benzene ring, and we are activating the benzene ring with that OCH3. So this is called anisole. That was one of those structures that we had to memorize as far as common benzene structures go. And we're going to react this with Br2 FeBr3. I'm just going to go ahead and add it in. Okay, well, what forms? All right, well, you'll look at this and you'll go, well, you know, the OCH3 is an activator, and that activator is going to go on to the bromine. Okay, well, that's great. Yeah, not a big deal. And then you would look at this and say, well, we can also have a para position. Okay, yeah, we can. OCH3 and a Br that goes there. And then some of you would write one of these structures maybe like this. Instead of doing an ortho to the right, you would do an ortho to the left. And that would still be ortho. It's still correct. You just wrote it in the opposite spot. So that's no big deal. It's still a correct answer. Now, the reason that I'm doing this is because we have an option here. We get orthos. We get paras. We regard them as separate products because they are. But what if I just really slammed this molecule with tons of bromine? I mean, I sucked it to it. Anisole didn't even see it coming. It was like one knockout blow, bam, of bromine right in its face. Because I've added so much bromine, look at this. This first product that we did, we said anisole was an ortho and a para. Well, if it has so much bromine and more bromine is still swimming around in solution looking for molecules to react with, that anisole is still an ortho and a para director. And if there's tons of bromine, hey, I'm an ortho director. I've got an ortho spot. Bing, another bromine can go on. Hey, I'm an anisole. I've got my para taken, but I've got an ortho spot. And we can have another bromine. And then, hey, I've got a para opened. We can have another bromine. And if there's still more bromine in solution, well, this anisole still has a para spot open. An extra bromine can go there. Or an extra one can go here. Or an extra one could go there. And we could actually place these groups on all of the ortho and para spots, believe it or not. We can do that if we have enough reagent in order to do it. So that's what this slide was basically telling us. If we take a benzene ring, now not just anisole, folks, all right? This is any OP director. Most of the OP directors, if they are given excess of the reagent, every single O and every single P can be taken by the incoming electrophiles. And that's what you're seeing in the product of 2,4,6 tribromo anisole. That's simply due because we had so much bromine in solution. It was looking for any O or P spot that it could. Now, what the book doesn't really go into is that metas can do the same thing. If I have a ring structure, and this ring structure has a meta on it, like an NO2, well, there's two meta spots. There's one here, and there's one there. Well, if I react it with just 1 mole of Br2 FeBr3, then only one bromine will go onto one of those meta spots. But if I give it excess, it will be just like up here at the top. Both of these sides can be attacked. That's because I simply have so much of that reagent that it's going to try to find any meta spot that it can find, just as it did with ortho and paras from up above. Now, we've talked a lot about nitros. We've talked halogenations now. You know, there were a total of 5 reactions that we talked about in the Intro to Benzene lecture. And what we haven't really discussed has been the Friedel-Crafts scenario. Okay, well, Friedel-Crafts scenarios, here's the deal with them. Friedel-Crafts were very, very slow. These were stubborn reactions that happened back in the day when we talked about benzene. So if I have a benzene with a deactivator group on them, any of those deactivators at the bottom of the chart, well, I've got a stubborn reaction. I now have lowered the reactivity of benzene. And if I try the Friedel-Crafts alkylation, which is adding an alkyl group, or Friedel-Crafts acylation, which is adding the C double bond O group, with those proper catalysts, reactions are not going to take place. It's not going to work. And that's simply because of the stubbornness of Friedel-Crafts. They're very hard to get to go. Now, this is only with the deactivator. So if I have an activator onto the ring, then ding, yes, they go forward. And they go forward just like you thought they would go forward in the past. We add on the alkyl group, or we add on the C double bond O R group. This happens just like it did with the benzene reactions. There's no difference. But I've just got to be careful. They go forward like usual with an activator. An activator will put these groups on the ortho or the para positions just like before. There's no difference. The rules stay the same. But if I have a deactivator on the ring, Friedel-Crafts is out of the question. It's not going to work. So keep that in mind. Don't let the example problems trick you, because they will try to. Now, let's take a look at another example. Oh, my goodness. What have they done to us now? Example problem. What products are formed? And it's a bromine addition, 1 mole. They give me A, B, C, and D. But the issue here is that there's 2 benzenes, not 1. What do they want me to do? I mean, we've not seen anything like this, and now they expect me to go from what we were talking about to this? So we're adding bromine, 1 mole of it only. So that means Br2 is going to be added. So I need to add a bromine onto these rings somewhere, some form, some fashion. There's got to be a product involved. So this is where this video is going to stop. I want you to take some time and I want you to think about where an incoming bromine would go if there's more than 1 ring like this. I mean, what is going to play the decision on where the bromine is going to be attached to? And the hint here is to go back to the chart. Go back to the chart and go back to one of those first example problems using the chart. Do you remember when it said A and B? Here's you 5 choices. Bromobenzene, toluene, chlorobenzene, xylene. Which one's going to be the most reactive? Which one's going to be the least reactive? Do you remember those questions? That's going to help you out. So take a look at A, B, C, D. Think about them. If you had to add a bromine, where would it go? You've got some choices here. What's going to play the deciding factor in determining where the bromine is going to get attached to in the product? So take a stab, hit play when you think that you've got it, and double check your answers with me. Let's see how clever you really are.